Bismillah ar-Rahman ar-Rahim. Our lecture today about the gradient and tangent to level curves. If a differentiable function f of x and y has a constant value, say, along a smooth curve r equal g of t times I plus h of t times j, which making the curve a level curve of f, then f of gt and ht equals c. Differentiating both sides of this equation with respect to t leads to the equations: the first derivative of f with respect to t equal the first derivative of c with respect to t, which leads to partial f partial x times dg times divide dt plus partial f partial y times dh dt equals 0. We can write this equation into two brackets: partial f partial x times I plus partial f partial y times j times dj by dt times I plus dh by dt times j equals 0. The first part is gradient f, and the second part is the first derivative of r with respect to t. The above equation says that gradient f is normal to the tangent vector dr by dt. So it is normal to the curve, which means that the direction r perpendicular to the level curve. To continue, at every point x naught y naught in the domain of the differentiable function f of x and y, the gradient of f is normal to the level curve through x naught and y naught. So, from the previous slide, the line through a point p naught x naught y naught, normal to the vector n equal ai plus bj, has the equation a times x minus x naught plus b times y minus y naught equals 0. Fn is a gradient, that's to say, the gradient f computed at x naught y naught equal the first derivative of f with respect to x computed at x naught y naught times I plus the first derivative of f with respect to y computed at x naught y naught times j. The equation is the tangent line given by first derivative of x computed, first derivative of f with respect to x computed at x naught y naught times x minus x naught plus the first derivative of f with respect to y computed at x naught y naught times y minus y naught equal 0. Let's show what we meant by the previous two slides through the following example. Find an equation for the tangent line of the ellipse x squared divided 4 plus y squared equal 2 at the point -1 and 2. We know that the ellipse is a level curve of the function f of x and y equal x squared divided 4 plus y squared. The gradient of f at -2 and 1 is given by the value x divided 2 times I plus 2y times j computed at -1 and 2 equal minus I plus 2j. Then the tangent is the line given by first derivative of f with respect to x computed at negative 1 and 2, negative 2 and 1, times x plus 2 plus first derivative of f with respect to y computed at negative 2 and 1 times y minus 1 equals 0. So substituting by the value negative 2 and 1, we get negative 1 times x plus 2 plus 2 times y minus 1 equals 0. Simplifying that equation leads to x minus 2y equal negative 4. Now let's consider the algebraic rules for the gradient. The algebraic sum of gradient of two functions is the algebraic sum of the gradient for each of them, i.e. gradient f plus minus j equal gradient f plus minus gradient j. If we multiply constant by a function, then the gradient k times f equal k times gradient f, where k is any number. Third, the product rules. The gradient of multiplication f j equal f gradient j plus j gradient f, similar to the derivative. Also the quotient rule, gradient f divided j equal j gradient f minus f gradient j divided by j squared. You may notice that these rules are similar to the rules of derivative. All what we considered in this lecture and the previous lecture for the two variables can be generalized for a function of three variables. So suppose we have a function f of x, y, and z, and the unity vector u1i plus u2j plus u3k in a space. Then we have gradient f equal partial f partial x times I plus partial f partial y times j plus partial f partial z times k. And the direction of f u equal partial f partial x u1 plus partial f partial y times u2 plus partial f partial z times u3. The direction derivative can once again be written as direction of f is a gradient f times u, which is the modulus value, the absolute value of gradient f times the absolute value of u cosine theta leads to absolute value of gradient f cosine theta. Now let's apply the previous rule here. In this example, find the derivative of f of x, y, z equal x cubed minus xy squared minus z at the point p naught 1, 1, 0, in the direction of v equal 2i minus 3j plus 6k. In what direction does f change most rapidly at p naught, and what are the rate of change in this direction? As we know, the direction of v is obtained by dividing v by its length. The length of v can be computed as follows. The absolute value of v equals square root 2 square plus minus 3 all square plus 6 all square gives square root of 49, which is 7. So the direction vector u equal v divide the absolute value of v equal 2 divided 7 I minus 3 divided 7 j plus 6 divided 7 k. The partial derivative of f at p naught are fx equal 3x squared minus y squared computed at 1, 1, 0 equal 2. And the first derivative of f with respect to y equal negative 2x can be computed at 1, 1, 0 gives -2. And the first derivative of the function with respect to z equal -1 computed at 1, 1, 0 gives -1. So the gradient of f at p naught is gradient f computed at 1, 1, 0 equal 2i minus 2j minus k. Then the derivative of f at p naught in the direction of v is therefore direction of u of f computed at 1, 1, 0 equal gradient f computed at 1, 1, 0 times u equal 2i minus 3j minus k, all this bracket multiplied by 2 divided 7 times I minus 3 divided 7 times j plus 6 divided 7 times k equal 4 divided 7 plus 6 divided 7 minus 6 divided 7 equal 4 divided 7. Point B. The function increases most rapidly in the direction of gradient f equal 2i minus 2j minus k and decreases most rapidly in the direction of negative gradient f. Then the rate of change in directions are respectively absolute value of gradient f equal square root of 2 square plus -2 to the power 2 plus -1 to the power 2 equal 3. And the negative of absolute value gradient f equal -3.